my colleague and department chair, Professor Alva Peled, and Professor Moshe Herzberg, who's also part of the Sustainability and Energy Center of the University. And we have here Meir with us, who's been our right hand during the organization of this whole thing. Our first speaker for today is Professor Ursula Eicker, whose CV, and correct me if I'm wrong, presents her as a German physicist. But she's been working on at the Concordia University in Canada for a number of years now, and her CV says that since 2019 she has led an ambitious research program to establish transformation strategies towards zero-carbon cities. Around 50 graduate students work on the paths of zero carbon cities in the domains of the built environment, renewable energy systems, sustainable transport, and circular economy. As you can see, technology doesn't leave any secrets anymore. Ursula, please.
All right. Okay. Yeah, thank you for inviting me to this conference. I mean, it's a bit of a change of topics, I would say, because I'm going to talk about cities, and we set up this big initiative at Concordia University in Montreal to bring everybody researching on cities into one institute, Next Generation Cities Institute, where we try to combine all the different perspectives on cities, built natural environments, the IT, mobility parts, but also, of course, the community building. And my work basically is on carbon emission mitigation, so climate change mitigation. So my team mainly looks at bottom-up carbon emission modeling in urban areas, and I'll show you a bit how we do that. And if you look at the picture, Canada is amongst the biggest emitters per capita in the world, on equal footing with the US. And if you look at the sort of lifestyle carbon emissions, so what every individual is really contributing, I mean, apart from the sort of public sector investments are not in the picture, but basically based on consumption patterns, including Scope 3 emissions. So you see, depends a bit on, of course, on the setting, but in the North American setting, transport has a very large share, followed by housing, but you see that nearly 50% of the carbon footprint of an individual is due to food consumption, goods, and services. So, and we are at 14.2 tons per capita, and by 2030 we should go to 2.5. I mean, a very big challenge. I mean, even the sustainable scenario in 2050 should be 0.7 tons carbon per capita. So we are a very long way off. But because this conference is not that much about mitigation, but a lot about green infrastructure, I show you a bit how we handle data and what we do with modeling. And of course, we also look at green infrastructure in cities and ecosystem services. So it's a bit of a I threw a bit together the different parts. My expertise is mainly in the carbon emission part, but with a biology colleague, I have some graduate students who look at urban green infrastructure services, especially related to urban heat islands, because as you know, cities are very built up now, lots of impervious surfaces, so there is a strong heat island effect. And of course, green infrastructure has also a big impact on air quality. So we try to look at all these connections between urban forms, urban morphology, whether it's built or green infrastructure, and the services related to it in a combined way. So in the end, we're trying to find the fair consumption space. So because there are still people in this world who are underserved, who really should have better access to food and minimum services, but the richer we are, the higher the carbon footprint. So there's also a lot of people who need to reduce consumption. And as you see already in this very small picture, it's a complex system that combines very many domains that we try to bring together. It's very difficult. I mean, even as a physicist who always claim to know everything, it's very hard to combine these sort of quantitative and qualitative indicators, because it's not just about the carbon footprint, it's also about how people react to certain green infrastructure. Do they walk more if they have street-level greenery? We try to find out these correlations on a quantitative basis, but also qualitative. And I show you a bit the tools, so going from sort of urban data analysis to more gamification approaches to see how people react to certain changes in the city layout. Because as you've seen, we are so far away from our goals, there need to be very drastic changes. So, digital twins, if you talk to geoinformation people, it's all about urban data. We have now 3D models of cities, and we can attribute these buildings with lots of information. But as I said, we can also integrate data on biodiversity, energy, and so on. So what we do, let me see whether that starts, yeah. So we have basically two different ways of organizing our user interfaces. This one is a web-based interface where we basically organize all data that we can access in a city. So it's all open data, so nothing is protected. And we do have from LiDAR flights, from different sources, photogrammetry methods, we do have 3D models now of pretty much every city in the world. So given that we know what the buildings look like, what the form is, and we have a few attributes on a city scale, like age, when it was constructed, and we know a bit about usage, we can actually model the energy consumption of every individual building. And then we could sort of add to this sort of map-based situation other layers of information. And it's not just data. I think that to me is important, because I think we heard it already today, that data basically describes the status quo. But how do we derive from data where we should go? So we need, I'm a strong believer that we still need models. And this, for example, is an agent-based traffic flow model that runs in the back end of our platform and shows you what the model choices, the model split is between different types of transportation media. And then we can change street layout, put more green in, or change whatever we want to change, and then see the impact on traffic flow. And it goes on. I wanted to advance that a bit if I can. Let me just see, just to show you at the end. We do also have a lot of information on the ecosystem. So there's a cartography, at least in Montreal, on public trees. We are still missing information on private trees, shrubs. We heard the importance of shrubs today, but there's already a lot of information, and we can overlay all these information in one platform, so that we can model, for example, the impact of trees on shading of buildings or on air quality.
I just want to take something really sorry.
Sure. Let me just go on. So this is one. This is basically the data platform. And just to show you some results from the let's call it the biodiversity group, we did, of course, some analysis of data correlating the surface temperatures, land surface temperatures, and the canopy index to basically find out what the impact of existing greenery is on cooling on the one hand and air quality on the other hand. And I mean, remote sensing data doesn't give you a very high spatial resolution, but it's so we complement that with ground-based sensor data measurements, and we try to find out what is the impact of composition, so distribution of green space, but also configuration. How are high trees spread over the city, and what is the impact on temperature? And here you see, I think, a very well-known result, that land surface temperature that you see on the y-axis versus high vegetation, basically trees, if you look at it on a borough scale, there's a very strong correlation, which basically means if a pixel on a borough scale is very green, has a very high percentage of coverage, basically parks, you get a strong decrease in land surface temperature. I mean, it can be up to 10 degrees or more. If you go to finer spatial resolution on the dissemination block scale, for example, you see already there's a much larger spread, because then you start seeing small parks in the street corner surrounded by high buildings, so that the temperature decrease might be high, but it might also be not very strongly affected by the greenery. So that's one result. Low vegetation is a more complicated story. The correlations are weaker than the tree correlation. But, of course, low vegetation has an impact on surface temperatures, and again, a big spread. So now we're trying to understand more in detail by going on ground of seeing what exactly the configuration does to temperature. But that's only one aspect. As I said, we also look at, does it induce people to walk more, if it's a pleasant green environment. So that's the sort of data analysis part. But as I said, in our platform setup, we also look at connections to modeling tools. And I mean, everybody who works on building energy modeling, we all have tools available like Energy Plus or Transys that can model the heating and cooling load dynamically for a city, and we use the same front end now to come up with use cases of, say, select an area in the city, give me the status quo, energy consumption for heating, cooling, electricity, and then do some scenarios. Build to code, retrofit to code, or retrofit to a very high efficiency standard, and plot the results basically over the year of construction of these buildings. Just sort of as a municipal strategy tool to plan and cost retrofit scenarios. You can do it per building type, say, give me all the hotels, or now Quebec wants to do a regulation on restaurants. And so I think these kind of tools help to quantify what retrofit scenarios really could do. And I don't want to talk about the details of the platform. It's a big undertaking to make an open source, very modular platform. I would be very happy if people want to collaborate, because we need to go across the domains, connect transportation, buildings, green space, and so on. All I wanted to say, so we need to have this, a big data handling part, lots of models from different domains, and then some clearly defined interfaces in the middle to connect to different front ends, that's the only thing the user will see and interacts with. And I just want to show you a few of the front ends, because that's probably where we define best scenarios and also start working on user interaction. And of course, the front ends also depend strongly on the use case, whether it's a citizen project or a municipal stakeholder or real estate setting. So what we can do with the tool on the mitigation part of the built environment is compare the energy performance of different urban settings, because we have a big debate in Montreal, how dense, how high, what is the most sustainable. And you see on the top here, anyway, you see on the top left typical plateau residential neighborhoods, 3 to 4 stories. Cooling, as you see, is not a big issue in the Canadian climate. But you see, I mean, on the heating load, just one small point, depending on orientation, it doesn't play a big role of whether you rotate the whole neighborhood more towards south or more towards north, because there's windows more or less on any of these sites. The biggest impact and the biggest message from all this is it makes a big difference whether the buildings are stuck together, lower transmission losses, or apart. So these sort of individual single-family homes, you immediately get double the heating demand. So I think that's also known, but we can now quantify that for an entire neighborhood. You also see that the downtown core has actually absolutely for both scenarios, sort of as it is and spares, a lower heating demand. Again, the same. The buildings are larger and more compact. So this is the kind of analysis we can do. We can do it, and we do it building by building. So in the end, we can go to every real estate person and say, okay, look at this building, that's the retrofit you can do. So, and now I want to talk a bit about the applications and the front end. So I showed you this 3D web interface. And the second thing we did, starting first with a competition project, is to say, well, now we have a building complex that needs to be retrofitted. And we wanted people in the neighborhood to play with the model. So we still do energy. We basically do life cycle carbon assessment of the project, also life cycle costing, but we want people to play themselves. So they don't know that there's Energy Plus and dynamic simulation in the back end running using this API. They basically say, I've got $10 million, who can bring down the carbon emissions the most for the least amount of money? That was the challenge, and we got actually a lot of people to play, and of course it's just simulation. It's not an optimization tool, so you can change whatever you want. You change the wall construction, you change the window types, you can increase the window surface areas. It all costs you money, of course, but it reduces carbon emissions. We also introduced renewables on the roof. We can put green roofs that might sort of increase your insulation performance of the roof. So we can do quite a lot of variations, and what you get out is the lifetime carbon emission. And so this was still a pretty simplified prototype, not that many materials included. Now we made a version more for professionals where you have the full ASHRAE catalogs of building construction materials, and you can really combine materials as you wish. Of course, there's predefined layers for people who don't know much about how to do insulation at all. As I said, you can also put solar panels on the roof. You can do some energy system variations and so on. So it already offers a lot of opportunities, and it's really simple to use. You don't need to be a building physicist. So you learn a bit of what certain technologies do to your overall carbon footprint and how much it will cost you. So that was basically the first time we went a bit into gaming. This is a Unity game engine that we used, and I show you where we took it from this very first prototype. So this is now the second prototype, and we designed this tool also based on Unity. Yeah, I think I'm going to do it in 5 minutes. So this is basically around our campus in Montreal downtown. So that's Concordia campus. So what we try to do here is to say, okay, we can calculate all these indicators, life cycle carbon emissions, maybe microclimate, air quality, lots of quantitative indicators, but how do actually people like what they see? If you change building heights, if you put more bike lanes, I mean, how do people accept it? Or what do they prefer? I mean, this question about height of buildings, density, very unclear, in my opinion, of what people really want. And it depends on who you are, whether you're a child or a single mother or an old person. So we have these versions. You can play different roles in the game, but you can also play as the city planner and say, well, now let's talk about density. Let's increase density in the existing stock, or put new buildings in the parking lots and so on. And as it is a game, you see you need to do a bit of work to unlock further levels. So at the beginning, you can just change the height and the usage of the building. And it does work. I don't know whether I can talk about it. I won't sing, I promise. So you change now height of buildings, and you get all these indicators on sustainability, but other indicators like green space, access to public transit, and so on. So here we changed this is more the city planner view. So you can select buildings depending on type, but then you zoom into a person and play a day in the life. Right? You get some tasks, and you, for example, here, the student needs to be in class by 9 a.m., and it has a few minutes. I don't know whether that, let's go. It's very quiet, I guess. Yeah, so now we want to have scores of how people like the environment they walk through.
I always love seeing trees, truly pleasant to the sight.
And the goal is to make the player as happy as possible, because that gives you eco credits to then do further action. So
It's not all that safe to walk here. Oh no, I don't have much time left. Ugh, I hate waiting.
It wasn't me who designed the high heels, by the way.
The city really should work on this public hygiene. Quite a nice touch of nature. I'm here early.
So then, depending of how good the experience was, you earn credits. You can then go to the next level and change more things in the city. So, I mean, as I said, we just started that a month ago. It's a very, very early prototype, but we want to really use that in the city to get feedback from the users of what they like and what they don't like. Okay, and I want to just finish off in the last 2 minutes. One last point on this combination of 3 models. Here we worked on an existing district and basically tried to look of what the inclusion of greenery would do to the indicators on microclimate and walkability. So we have now different tools to generate different configurations of geometry, but also of greenery, so of low, middle, high shrubs or trees and so on. And just of course, it has an impact on the detailed temperature distribution. So we model then the temperature distribution, wind flows in the canyons and so on in these areas. And in the end, you get some quantitative information of how a certain tree coverage for example, along the pathways changes temperature levels, so makes it more comfortable to walk. It's one thing. Whether people do walk more is, I think, a different story. So that's why we want to have these other approaches going beyond the quantitative information that we can calculate of seeing, do they really walk more? Okay, and to get that all into practice, we also work with the stakeholders, I would say, in the city. And one idea, because things are moving very slow, we're never going to get to the 2030 goals if we continue at the pace. So one of my activities is to bring decision makers together. We call it a SWAT team, to sort of a banker, the utility, Hydro-Quebec, the city, and a real estate developer, to say, okay, give us all the barriers to a more sustainable project, and then if it's financed, the banker has a green bond. And if it's a city for zoning, the city is at the table and they need to really support the project. So we will do 2 projects every 3 months, starting basically now. And I think that's our attempt of going beyond modeling, of bringing real change to the city. So to conclude, I think the simulation is useful because it helps, on the one hand, to quantify, but via these sort of game-like tools, also maybe to get a feeling of what people prefer. Better than surveys, I would say. They can, I mean, in the end, they will have virtual reality things and really walk around the areas and give us feedback of what they prefer. Yeah, and whatever we can do, I think we need to bring in all these different methods to achieve faster rates of decarbonization, because I still believe in mitigation. Thank you very much.
Thank you, Ursula, and thank you for keeping in time. And I would like to suggest that we keep all of our questions for discussion at the end so that the last speakers do not end up by having to speed up. Our next speaker, Professor Susan Roaf. Yes, that's it. from Harriet Watt University in Edinburgh. Sue has a very rich curriculum vitae of both academic work and research, as well as, how shall I put it, public interference. She has been a member of the City Council of Oxford for years. She's published a number of books on eco-houses, climate change, thermal comfort, and is member of a number of initiatives, international and national.
Thank you, Zaki. That's brilliant. I've got a very good contrasting presentation to yours. Yours is very high-tech, smart end. Mine's rather stupid, low-tech end. I'm talking about passive survival, and consider me as an ambassador of the future. I'm usually about 10 to 15 years ahead. We live in a very fast-changing world, and I'm going to talk today about building sufficiency and resilient comfort in a desert context. Now, this is the IPCC 2022 Climate Change Report, version 3, mitigation, and the predictions are really alarming. And if you look here at the, is that right? That one? Yeah, look here, we're looking at 3 to 5 degrees centigrade on current projections, increase in temperature. We're 1.5 now, and look at the climate catastrophes that are already hitting, climate catastrophes that are already hitting us around the world. Records broken almost every day. And of course, the accelerated warming in the dry regions is going to be a real challenge, and as we heard. Now, what about temperature? Temperature kills. The 2003 European heat wave, over 72,000 people died in buildings during that one event. In 2022, we had some heat waves across Europe, and over 20,000 people died in buildings during that event. And the 2003 heat wave by 2050 will be a cool summer. So let's talk, in real terms about what's happening. It doesn't matter how rich or poor you are, it doesn't matter where you are, these weather catastrophes, extreme weather events will hit, and they will be associated with grid failures. That's inevitable, whether you're in Kiel, North Germany this year, in Texas, with ice storms, or under a heat dome in British Columbia in Canada, where temperatures reach 43. Business as usual policies are failing. And we can see from this current path where the trend from implemented policies, we're just really fiddling as Rome burns in a way. We're sort of pretending that we're doing all right. Now look at the report from April on mitigation from the IPCC. These reports are always done with vested interests, often in the driving seat. And on one hand, these reports promote technology. And you can see here with the shelter, the buildings issue here, we have got social practices, lifestyles and behaviors. We have got compact cities, rationalization of floor spaces, architectural design like heights or so on, urban planning, green roofs. There are a lot of product-related or approach-related solutions there. They don't mention things like running buildings on natural ventilation or systematic application of shading. And energy efficiency figures very largely. The heat pump industry is very good on that, the high conditioning, the air conditioning, and they're now pushing a lot of mechanical ventilation, heat exchange, and in Britain they're pushing hydrogen technologies. On the other hand, they are showing the growing problems with these approaches. Look at the increases in ozone-depleting F-gases, absolutely exponential increases. And in the mitigation plans propose efficiencies And you can see here in the building section, building design and performance, on-site nearby production of renewables, change in construction, circular economy is another product that has been heavily pushed, and change in construction materials. And high efficiency heating, high efficiency envelope, high efficiency appliances. Where are things like running buildings on natural ventilation? Where are important passive design features in that lot? Now, buildings are responsible for 31% of global final demand in energy, 21% of global emissions, CO2 emissions. Residential buildings are responsible for about 70% of global final energy demand for buildings. And between 1990 and 2019, CO2 emissions went up by 50%, and electricity used globally by 161%. So what's happened to all the billions spent, billions if not trillions spent, on the big projects across Europe, across Meir? Where have they evaporated to? They're having no results. So why? Here we are using a wide range of demand-side opportunities. This is from the IPCC. What are they? Demand side, improve heat pumps. Surely that's the supply side, refurbish and renovate renewable electricity. This is all product dominated. And there's no real demand side features in there. Why not, again, say naturally ventilate buildings for as much of the year as possible? Why not say design energy sufficient building? Why not put in, again, mandatory shading? No, it's all product related. And there's a good reason for this. It's not ASHRAE, its first meeting, 1895, in the core constitution, designed at the first meeting, said to establish clearly defined minimum standards of heating and ventilation for all classes of buildings, and to favor legislation compelling ventilation of, in brackets, mechanical servicing of buildings in accordance of the standards of this society. And they have done brilliantly. They have changed global standards, so it's created a generation. If you look at the traditional naturally ventilated buildings, you can have good and bad performance of them. This is from 1990. We knew back then. This is 1960s naturally ventilated. This is standard air-conditioned buildings in terms of energy use, and this is large prestige glass buildings, tall or not. So we got from the best of these naturally ventilated traditional constructions to there, you got 4 or 5 times more, and they are sold as efficient buildings. This is the energy efficiency floor, right? It is possible for a building, vehicle, or system to be highly energy efficient, while at the same time to be highly energy consuming. And by the way, if you want the slides, I put all the references for this. And here's the embodied energy issue. Every floor you go up, in a building, you're talking about high-rise buildings, every floor you go up costs more to build per meter squared. That's obvious. But this is a really excellent study, again, done a long time ago, 2001. And look at Beersheba in the 1960s. Look at Beersheba in 2020. Any city you go to in the world, you can almost date it by looking at the building, what date the building is, because it's a certain type. Being pushed towards that high-tech end. And I mean, look, if we look back, say, at the Negev, we had the traditional buildings until about 1950. We got the introduction of a world in which energy was going to be too cheap to meter, built on the fossil fuel industry. These are the types of buildings that gradually grew up until we got post-1950s. We've grown into a world in which normalizes the highest energy building types on the planet. for use by the rich. Only the rich live in these or work in them. And then we overlay that with standards, rating systems, that greenwash, systematically greenwash buildings. LEED is the worst. And you couldn't get a LEED Platinum unless you had full centralized air conditioning, as Edna Shaviv pointed out very carefully. This was written by, originally run by Rick Fedresky, who's the environmental chief lead at Carrier Air Conditioning. So you couldn't get LEED Platinum without something like. And models are fine, but the performance gap, this is assumption-dependent design modules. So they model in BREEAM or a complex model, which really rarely reflect the actual performance of a building in use. The future has to be different. It has to be very different if we are to survive, if the planet's to survive. And IPCC's recognized this, so we're going now into sufficiency. Building sufficiency is put at the top of the list, right? Above efficiency and above renewable energies integrated. Sufficiency measures tackle the causes of greenhouse gas emissions by limiting the demand for energy and materials over the life cycle of buildings and appliances. And that's different from energy efficiency. In contrast, is about continuous short-term marginal technological improvements. Sufficiency, energy-sufficient buildings, sufficiency is about the amount of something that is enough for a particular purpose. And early publications on sufficiency, or recent ones, this is 2018, buildings should provide enough room for you, provide security, usability, and a certain level of comfort. So comfort should be at the heart of the building solutions, right? We have to have buildings that provide acceptable comfort temperatures. So what is an acceptable comfort temperature? Now, there's two methods of looking at this. There's the engineering, the HVAC engineers measure, which is based on a heat balance method. Typically like PMV, 4 basic physical parameters and 2 assumed levels of clothing and activity, based on very limited and often quite poor and dated laboratory research. These steady state conclusions are. They come up with very limited comfort temperatures. So for instance, they promote more HVAC in buildings by grading buildings, like an office building. An A-class office building has a very narrow temperature zone in winter and in summer. The narrower the zone, the more HVAC you need, right? So an A-class has to be a really high-tech, fully equipped, air-conditioned building. A C-class, which is third-class building, has a much wider range. So first class might have 21 to 25, and a third class building might have 19 to 27, so you can have that internally. There's troubles with very tightly controlled buildings, which, sort of thin, tight skin envelopes, is that when the grid fails, you have to get out of them. And that happens across the world all the time. Problem 2, ACs use excessive energy and make higher emissions. So here's work from Berkeley showing that you can get, easily, sort of 10% efficiency just by simply widening. They're doing this in a lot of countries. Netherlands now has mandated 18 to 28. You can have anything in that range in their government buildings. Italy's the same. So you just simply set the thermostat lower in winter and higher in summer, and you can save easily 8 to 10%. Third problem with it is that the ASHRAE standards have led to significant overcooling of buildings. In America, $10 billion wasted simply by having buildings that are too cold. And number 4 is that it's fine promoting and pushing efficient technologies on people like hydrogen or heat pumps. People can't afford to eat. In Britain today, So how are they going to afford to buy a £15,000 heat pump, let alone run it? So, people have to get real. The second way of measuring comfort is the adaptive thermal comfort, which came out of work from the 30s onwards in the BRE in Britain. And they showed very early on people can be comfortable from 38 to much lower temperatures, 18, 10. And so Fergus Nicholl and Mike Humphreys, who I work with, Fergus Nicholl did this wonderful comfort as a dynamic feedback system, and Mike Humphreys showed the algorithm where the indoor air temperature you're comfortable at relates to what climate you're in. So the hotter it is outside, the hotter you're comfortable at. It's pretty simple, but he provided the algorithms we can use. You just go into real buildings, you do a comfort survey, ask how people are feeling, what their controls are, is the window open, is the blinds down, ask about how comfortable, note their clothing, measure the environment. And out of that comes a lot of data from which you can extract the algorithms statistically, or you can look at comfort clouds. Now, this is a study of thermal comfort in countries across Europe, and you can see these comfort clouds. People in Pakistan can be quite comfortable from 10 to nearly 40. People in France, they heat in the winter, they naturally ventilate in the summer. In Portugal, they naturally ventilate all year, they get a bit cold. In winter, Britain's all over the place. In Sweden, it's a cold country, they just have heating on all year, and they have 20 to 25 typically. And if you look at these comfort clouds from Pakistan, Tokyo, Shanghai, England, Melbourne, these are the comfort envelopes people live in. International standards are a form of comfort colonialism. They take the ASHRAE standards and apply them to India or Africa. But comfort is what we do to avoid discomfort, to keep our deep body temperature at 37. We interact with the world around us, and we can calculate this. We have involuntary actions of the bodies, like when we're cold, we shiver, and when we're hot, we sweat. Physiologically, we adapt. The naked body doesn't need to do anything to keep comfortable between 28 and 33. We change our clothing and activities, and we exploit adaptive opportunities, open a door, window, fan, etc. Change rooms, change places. The principle is people adapt to those conditions they occupy, or else if they're not comfortable, they change them within limits. And here's the limits. From thermal comfort studies around the world, people can adapt fairly easily anywhere between 10 degrees centigrade indoors and 35 degrees outdoors. Now, if anybody's interested, I will show you how we use Nicholl graphs. This is a Nicholl graph from Beersheba for pre-1990, and it shows that we got maximum temperatures of about 32.6. And that can tell us what sort of building is suited to the Beersheba climate. The roles of, for instance, thermal mass or natural ventilation in heavyweight buildings, as you can see here, which keep very stable thermal indoor temperatures, or lightweight ones, tents or sheds. This is work done by Saki. But look at Beersheba in 2007 to 2021. We've got, this is widening, the diurnal range is widening. The maximum's going up by 2 degrees centigrade, minimum's up a bit by 0.5, and the mean of the indoor temperatures is up by about 1.8. So in Beersheba, you are already adapting to different indoor temperatures. And what we have to do, buildings for the 21st century will inevitably, the HVAC building is a dream of wet dream of the 20th century HVAC industry. That's already business as usual. The future has got to be mixed mode, so you use cooling and heating when you need it. You can use personal comfort systems for much of the year as well. Or you can simply open the window and rely on natural ventilation, shutters, shades for as much of the year. This minimizes your energy use, because the difference between what you need and what you want can be seen as a measure of sufficiency in terms of comfort. Buildings in a heating world with ever more extreme weather, what you need is what will keep you thermally safe in the building you're in when the grid fails during extreme weather. You can do it with passive design. Horizontal thermal landscaping within buildings is incredibly important, so you occupy a cool zone in summer and a warm zone in winter. Vertical thermal landscaping through a building is incredibly important too, so you have to know about ventilation in buildings and understand time lags. Yep, okay, my time is up. Understand time lags, because you're deep down in the earth, you're going to be, the temperature's a month away from what's outside, so you've got some resilience. Get the windows right with secure shading. Create comfort zones, shallow plan buildings so you can naturally ventilate. This is the movement. This is Singapore. Low energy personal comfort technologies for much of the year when you need them, to avoid having to put the air conditioning or the full heating on. Because buildings must in the future be able to be run for as much of the day and year on local, free, clean energy. And hot, dry climates have particularly dangerous temperatures. So as Ursula was saying, you have to have cool cities and communities. And I've got lots of links to YouTube talks, cool systems around buildings. Future cities will have to be energy sufficient, not energy efficient. Passive survival buildings run on local energy, buildings for people and the planet, not for development profit. Thank you.
Buildings for people, not for development, for developers and profits. This is a nice opening for the next presentation. Our next speaker is David Pearlmutter. Professor David Pearlmutter is an architect from the Ben Gurion University, desert architecture and urban planning in the past, and geography currently. David has a long history of working on pedestrian comfort, thermal comfort in open spaces, sustainability, and adaptation of building and design for drylands, hot climates. David, please.
Thank you very much, Saki. And thank you to the organizers and Sue and Ursula, our previous speakers. I'm going to be looking at cities where more than half of our species now lives, and the proportion is getting higher. And I'd like to start by showing you a picture. And those of you who are from Israel will probably recognize this immediately as Rothschild Boulevard in Tel Aviv. And what I'd like you to do for just a moment is to try to imagine this scene just as it is, with all the activity. We have cars and we have buses, we have bicycles, we have people sitting, we have people walking, some for leisure, some for exercise, and some actually in order to get from point A to point B. I would like you to imagine this picture without any trees, just as it is, but with no trees. And I want you to ask yourselves, with the activity taking place here, would it change or would it continue on just as it is? Could it? So my answer, could it, is yes. The traffic could continue, people could continue to walk. The question is, would they want to? And if they would not want to, how many of them would prefer to hop on a bus, unless the bus stop is too far away? We're talking, of course, about a hot summer day here. How many of them, in that case, would get into their air-conditioned private car? or how many of them might just stay in their air-conditioned home or air-conditioned office. And I don't think this is just a matter of comfort. This is a matter of thermal stress. Our cities are getting warmer. We've heard about heat island effects. This is on top of regional and global warming trends. So I'd like to ask a couple of questions here. First of all, how is our behavior actually influenced by this thermal stress and the design of our urban environment? And how can we make our pedestrian realm more resilient? We can't pretend that changes are not happening, but how can we be more resilient to these changes? So the first answer that we usually come to is what we've already heard about, green infrastructure. That is trees and green spaces in the city. And this is nothing new, because as long as there have been cities, there has been this need for a sense of nature within the city. But nowadays we think of green infrastructure as something more tangible, just as essential as running water and electricity and communication. And it provides a range of different ecosystem services. So just as an example, our green spaces filter pollutants in the air, in the soil, in the water, also mediating flood risks, enhancing biodiversity, especially in places where it otherwise would be lacking. And what we're talking about here, this is also an ecosystem service, moderation of human thermal stress. And when we talk about this moderation of thermal stress, in hot conditions, we often talk about cooling the city. We talk about temperature, we also talk about humidity of the air, the rate at which the air flows, the wind speed. But how much cooling do we actually get? A greener city, we saw some evidence before, a greener city lowers land surface temperatures. But how much does it actually influence our sense of comfort, our thermal stress? And how much is this actually a function, at least in our part of the world, in dry lands, in arid and semi-arid regions, such as basically all of Israel? How much is this really a function of radiation? How much is this a function not only of the radiation that our body is absorbing from the sun, but also what's reflected from the ground and what's emitted from surfaces that are soaking up this solar radiation? So in a word, we're talking about shade. Very, very simple word, a little bit less simple when it gets down to it. But what we found over and over in previous work is that on clear summer days, our perception of comfort is dominated by exposure to solar radiation, sometimes though in a less than systematic way, more of an intuitive way. A problem with shade trees, especially here, especially in the Negev and certainly in all of Israel as well, is that trees are expensive. And I'm not just talking about the cost of a tree, I'm talking about providing sufficient soil volume, sufficiently soil that's not compacted, maintenance, of course, irrigation, which is needed just about anywhere in this country, pruning. So trees are valuable. You can see here the effect of a single tree on ground surface temperature, almost 20 degrees different between what you have on the ground in the shade of a tree and in the middle of an asphalt street. This affects what we feel, but it's not all of what we feel. So how can we provide maximum, how can we provide shading for the maximum benefit, okay? So to answer this question, we've been working for the past several years now on a project. This is funded by the Israel Science Foundation. And what we're doing is we're developing a tool, a microclimate analysis tool, to combat urban heating so that we can help urban planners, decision makers, let's say, get more bang for the buck. In other words, prioritize their interventions in urban trees and green infrastructure. This is an ongoing project. I'm going to show you the first two phases of it here, and the third phase is near completion now. So in the first stage, we did a very, very extensive monitoring campaign, measurements in the city of Tel Aviv. The purpose of this is to calibrate a model, which will be part of the, ultimately the design tool that we'll be offering. And in order to do these measurements, what we want to do is measure everything necessary to be able to express the physiological thermal stress of a person. So we built this mobile weather station, which measures temperature, humidity, wind speed, but very importantly, it measures in 6 directions the entire radiation field, shortwave radiation, long-wave radiation, so we can get a full picture. And as you can see from just a handful of examples, the goal here was to get the widest possible diversity of different urban spaces, shaded, unshaded, different surface cover, whether it's grass, whether it's artificial grass, or whether it's asphalt, concrete. And you can see from the map the distribution of points where we measured in summer of 2020 in Tel Aviv. We also had a stationary weather station on the roof of a City Hall building and a portable station. So, very briefly, what do we find? What we see here on the y-axis of all these graphs is what's called the physiologically equivalent temperature, and this is one of many comfort indices, so-called comfort indices. This is not air temperature. This is an expression of the entire energy balance or exchanges of energy between a person and the environment, mainly by radiation and convection, but it accounts, for example, of heat loss by sweating. So it essentially quantifies how much cooling by sweat evaporation under warm conditions we need to stay comfortable. So let's see how this comfort index correlates, first of all, with air temperature. Not so well. What does that mean? Does that mean air temperature doesn't affect comfort? Of course not. Temperature, of course, affects comfort. But the variation in air temperature during different times of a summer day and between different points within the city is relatively small, and that is not the main thing driving differences in thermal comfort. Same thing with relative humidity, not a very strong correlation. Even wind speed, which is a bit more localized, still not a strong correlation, but with solar radiation, we see a much stronger connection. And the strongest of all, we saw before reference to the mean radiant temperature, which is what expresses essentially the entire radiant field. So solar exposure quantitatively, systematically, is indeed responsible for most of the variation in stress, and the other differences are less influential. So if we know that shade is so important, do people take advantage of it? And this might seem like a very intuitive question. How many people actually walk, travel in the shade when it's available? There's shockingly little quantitative, systematic evidence to tell us how much they actually do. So in the second stage of this work, which was led by Michelle Levinson, we actually observed people on a very, very large scale, again in the city of Tel Aviv in the summer. What we did is we took essentially time-lapse photography or high-frequency photographs of strategically selected points in the city, usually where we could identify shaded and unshaded locations within the same view. We used these screen lines here to count pedestrians walking in different locations, and we quantified the volume of pedestrian and bicyclist traffic different times of the day and, of course, in different locations. So what did we find? Top line, do people walk in the shade? Well, if we take our entire overall sample, during the hot hours on a summer day in Tel Aviv, all else being equal, about 60% of the people are walking in the shade. What about that other 40%? They're in the sun. And at this top level, we also don't see much of a difference between pedestrians on foot and bicyclists. And this is a quite large sample, over 5,000 people who are identified from, I think, 60,000 individual scenes, which Michelle embodied our automated system for accounting pedestrians. Could give you more details on that. I think what's much more important is that not every location has an equal opportunity of finding shade. Some have more or less shade within the same location. So we classified locations into shade availability categories. So as you can see here, the more shade there is, the more people will use it. That should be clear, but I'd like to focus on this intermediate category, number 3, in which we evaluated the space as having a relatively equal amount of shaded area and unshaded area. And then the proportion of people walking in the shade goes up here to 65%. If we look only at pedestrians on foot, it goes up to about 70%. You can see here in the map that the preference for shade is relatively widespread, equally distributed within the city. There are some points where a majority, even under equal circumstances, a majority of people are in the sun because there are always special conditions. What's most interesting for me is when we compare locations with different proportions of people in the shade and the sun, to what extent is that a function of the actual conditions? In other words, if it's the hottest part of the day, if it's the sunniest part of the day, or if it's the late afternoon, when both the temperature is high and the absorption, the exposure of a person to solar radiation is at its peak, will that influence people to perhaps even go out of their way to find the shade? So the answer is yes, there is a signal here. There's a relationship between the solar exposure of a person and the proportion of pedestrians who are in the shade. Solar exposure is a bit detailed here because we account not just for direct radiation from the sun, but also reflected radiation from the ground, diffuse radiation in the sky. So we get a signal, we get a relationship here. I'm not going to present it here, but I could show a lot of correlations in which there seems to be no connection. If we just look at air temperature, if we just look at the intensity of solar radiation on the ground, etc. At midday, at high noon, as you can see in the photo, it's quite a bit easier to keep yourself in the shade. The other thing you see in this photo is our portable station, which complemented our mobile station to get more precise localized data. So to sum up, this in a sense confirms what we suspected, but in my opinion is the first time that we've been able to get a quantitative and systematic set of evidence for it. But it increases our confidence in suggesting that if urban planners, decision makers, those who prioritize interventions will actually provide better shaded cities, people will in fact use them. They have the opportunity. I'm going to mention a couple of things with the time I have left. One is a book called The Urban Forest, which had close to 100 contributors from all over Europe. And if anybody's interested in this particular field of urban green infrastructure, this is sort of the state of the art on the environmental, social, and governance aspects of urban trees and green spaces. And the International Association for Urban Climate has a quarterly online newsletter. Anybody interested in urban climate should definitely check this out. And since I've been editing this for quite some years, I'm always interested in contributions as well. So thank you. Short and simple.
Right. Our next speaker is Professor Denia Kolokotsa from the Technical University of Crete. Denia is also the head of the School of Chemical and Environmental Engineering, has a significant number of international prizes that she has won, and I had the good luck to collaborate with her during my past sabbatical. Denia will be talking today about cool roofs in Europe. It's a big topic in Israel as well. What is a cool roof? Is a green roof necessarily a cool roof, or is a cool roof necessarily something that is, on a life cycle energy analysis, worth the trouble? Denia, please.
Thank you very much for the invitation. Thank you, Sykes, for the introduction. I am very pleased and happy and honored to be here today with you. I'm going to speak about cool roofs, but not only roofs, but also materials in the urban environment. They started with roofs, the cool materials. That's why we talk about roofs, but it's not only roofs. And since I was, for 10 years, the president of the European Cool Roof Council, I would like to tell you a bit of some insights of the work that we've been doing to mainstream Europe. So the challenges for, this is the change of, okay, so the challenges that we have for cities are already mentioned by the previous speakers. We expect the cities to expand by 80% the next period, and the global 80% of GDP is produced in cities, and also 70% of the energy consumed in cities, and 75% of waste and greenhouse gas emissions are emitted. There is a lot of discussion about cool roofs and cool materials. You see here some November 22 discussions in Australia and in other places in the globe about the necessity of cool roofs and materials and how they can help us in the energy crisis. So I'm going to talk to you about now what are the strategic decisions of Europe and goal, and what we are trying to do to mainstream some research towards cool roofs. So I don't know if you heard about the well-known Green Deal, which it's in a political agenda for the European Commission until 2024, and also the mission of climate neutral and smart cities. We aim at the decarbonization of cities. This is something very important for Europe, but of course we face also the energy crisis now. I would like also to mention the new European Bauhaus initiative, that is an interdisciplinary initiative that connects all European strategies for outdoor living conditions and spaces and experiences and cities. So we don't talk only about sustainable cities, but in the new European Bauhaus, we talk about enriching, so aesthetically acceptable cities, which is something very difficult because it's a subjective issue. Sustainable, in harmony with nature, the environment and our planet, as also mentioned by David before, that is something that we want. And inclusive, so we encourage the dialogue along the cultures, the disciplines, genders, and ages. That is something that we need to promote all these aspects. So I would like to explain a few things about cool materials. Cool materials, they have three main properties that are assessed. The first is the solar reflectance, the amount of solar that is reflected back from a surface. We want high solar reflectance, we want high infrared emittance, so faster release of heat that a surface can take. So we have lower surface temperatures, less heat that penetrates into the building, less heat that is transferred to the ambient environment. There is also one other index that is very important. This is the solar reflectance index that compares the temperature of the surface with a completely black and a completely white surface. And sometimes, if we have a very good cool material, this SRI can be higher than 100, can be 120, 115, 114, that I've seen some materials that they have lower surface. So to mainstream our work, we see that in various countries in Europe, there are different policies, different promotional activities, different case studies. In Greece, for example, we had in our national law the promotion of cool materials in buildings, in Italy also, in Spain. But we wanted to do something to mainstream the work for whole Europe. So we tried to follow the route of what is called a Sense and Elect workshop agreement. That is a reference guidance that contributes to raise awareness and promotion the use of cool concepts and products among various stakeholders. And this is released this September after 2 years of work. Actually, I have to mention that the last time I was in Israel, I had to fly immediately to go to Brussels because we wanted to set up this Sense and Elect workshop agreement for cool roofs. So it's good that now, after all these years, I conclude with presenting you this. And in this, we started with a group of 10 organizations discussing this around Europe, and then we ended up with more than 25, 30 that participate in the consultation. We realized that there is a benefit of standardization for research and innovation. You see here the loop that goes from research questions to applied research, then to experimental development, then to market and try to market and maintenance, and then in order to go to the market, we need to have some validation, innovation, and standardization. And standards give access to the state of the art, so you don't have to reinvent the wheel, and ensure compatibility, comparability, and interoperability of innovation that is already available in the market or wants to go to the market. So to face the challenges, because there are different approaches, what is cool materials, what we accept, we want there's first of all fragmented markets, limited holistic approaches. We want to have political long-term engagement, and there is a lack of new business models and financing solutions, need of knowledge sharing and boosting innovation to market. So that's why we use this way. So I'm not going to go into detail, there are 3 phases. You prepare the documents, there is a production phase there. First of all, it's a preparatory phase that everybody meets and sets up the discussion points and technical details that are going to be put into the essential and electoral agreement. Then is the production stage that we work on drafting the documents, finding references, discuss with people, and then go to public consultation, which is a very important step. And then we have approvals, different stages of approvals by CEN, which is the Center European for Normalization, or also by various other bodies that want to go ahead and speak or have some objections about the documents. And then we had the final application, which is valid for 2 years, then can be extended in more than 2 years, and then can become a standard, official standard of Europe. This is all the work that has been done. So what we're going to discuss is similar and related standards, the benefits and limitations, properties, and what is happening in building and district level. The good thing with this approach is that we mapped the different technical documents and standards that are related to this mitigation of urban heat island effects with cool materials. This is how we call the Sensenelec. And we relate it to the buildings and systems with thermal insulating materials, products, and thermal performance, with roof covering products, with sustainable smart cities and communities, SEN standards, and sustainability and construction works. There are more here to see. There are other also standards. This is good that we mapped all the standards that is related and are interrelated with this aspect. Then we had to go ahead and look what are the benefits. And we have environmental benefits, energy benefits, social benefits, economic benefits, and some of them that are based on existing case studies. That's just representing you. A lot of work has been done behind that. Is first of all that it's a reduction of energy consumption of buildings by 20%, depending of course on the envelope that we have. It's a mitigation of urban heat island by reducing the surface temperature for more than 25%. I will show you some case studies for that also. It reduces the peak power plant requirements by 0.7 as an average kilowatt hour per square meter of city and degree of temperature increase, while the average is a peak electricity demand is estimated close to 21 watts per degree temperature increase and per person, and of course contributes to a reduction of carbon emissions as an average by 5 kilograms of CO2 equal per square meter of albedo or reflective index increase. What are the social aspects? Improve thermal comfort, reduce health risk in cities, which is considerably higher than the rural environments, and also that things that are related to the outdoor comfort. tackling energy poverty by low-cost energy innovation, something that can be applied easily. We have some case studies at the Southern America, in Brazil, and other areas for low-income population that they don't have insulation, and there's a considerable increase of thermal comfort. There's economic benefits, because I don't know, this is something that can be, it's something that is, can be discussed, but maybe it's increasing the value of asset in real estate market, reduces the energy bills, of course, this is for sure, and improves the performance of rooftop photovoltaics, because it lowers the temperature of the roof and then increases the efficiency of photovoltaics that's on top. So there is a market around the globe. Here are some companies. I don't want to, there are some companies also giving some details about the quoting market. It's an expanding market, it's worth $3.5 billion in 2019, and is expecting to rise more and more, and I have more data on that. So I would show you 3 case studies that is developed in the last period in a European project called Recost. One is in Spain, the other one is in London, and the third one is an urban environment we try to do in Hania, Greece. That's where the university I come from is based. So the first one is a building in Cadiz, Spain, and you see here the facade of the building. So the total building area is almost 2,000 square meters, where the area that people live is 1,500 square meters, is 5 floors and 28 habitable apartments. You see here on the right a model of Energy Plus. That's already mentioned that we use these kind of models to assess. You see the application of the product on the roof. There is some details, technical details about the roof, and the properties of the cooling roof is solar reflectance 0.89, infrared emittance 0.89, and solar reflectance index 115, which is quite good. And we use different liquids that are mixed and then is applied in different layers. And you see here before and after. This is simulation, but we also measured the surface temperature because I wanted to show you in the same time. We also measured, so you have here the surface temperature before and then after. And in most cases, with measured results, the cool roofs have lower temperature, at least 10 to 12, 15 degrees. This creates a reduction of the energy consumption for the total energy consumption. There is also here some cooling, some load penalty, because if you lower the surface temperature of the roof, you increase the heating energy requirements, but depending on depending on the climatic conditions, this might be 0 or very, very little. And also, there are studies that show that even in climates in the center of Europe, for example, in the Netherlands or in Germany, if there are high internal loads in the building, the application of cool roofs at the roof may make the difference between using or not using air conditioning while the buildings are operating, especially if it's in industrial buildings. The second case study is in Brunel. We also modeled the building here. It is a state of Brunel University in London and is used for student accommodation, and total building area is 4,700 square meters. Here you see they did some, there we have area that is applied with cool roof and area is not applied with cool roof, so we used different 16 type K thermocouples were installed in the roof to monitor the temperature difference between the painted and unpainted side of the roof. You see here different properties: solar reflectance 0.87, infrared emittance 0.9, and SRI 110. Why we didn't use the same, might ask, because this is given by the companies, so we spread the materials around the different case studies. And the initial plan was to install thermocouples on the inside ceiling to measure the air temperature, but this was not possible due to COVID-19 restrictions, and also there are no people there inside during that period to monitor their comfort conditions. Here you see the monitoring results. We have this green line is the solar radiation during the day. We have the thermal zone temperatures and baseline and cool material. You see here what is the difference between, it's at least 1 degree difference, 1.5 degree difference between the baseline and the cool material. And you see here, this is surface temperatures, and this, it's indoor temperatures. And then you see here the outdoor air temperatures. So now we see here the surface temperature measured by the thermocouples. But we can compare this because we have the two roofs, and the difference is quite high, as you see, with the cool roof and without the cool roof. This is at the middle of the day that we have the higher temperatures. The difference is at least, it's very high. It's, it's impressively high. And I will end up with a case study in Hania. You see here that we tried also to combine green with cool because it's aesthetically more acceptable instead of having these tiles of cool materials. Here you see an area that we wanted to study. It's on the center of the city. You see a stadium, and there are the schools here. And this area that there are the schools, there is no shade. There are no trees. So the students do not want to stay there and go within, they do not want to stay outdoors. So there is a study that we did with air temperature in existing conditions that you see here, that during summer it goes, the air temperature very, very high. At some points is between, I'm finishing, 37 to 39 degrees, especially in hot summer days. And then you see the surface temperature in the existing conditions, which if you see here, it goes at some point to 54 degrees at the midday in July, 54, 58, sometimes even higher. And then we apply, we try to see what would be the impact of cool pavements. And we see that there are, you see those lines, oops, no, what did I do here? You see those lines that we applied, we tried to apply the cool materials. It's not a big change because we cannot dig and change everything, but wherever you put a cool pavement, there might be a surface temperature between 8 to 12 degrees difference of temperature, of surface temperature. That creates a better comfort conditions at the ground level. And of course, if you have said, I completely agree that we need to have urban infrastructure, urban green infrastructure in our cities, then we create very pleasant environments and aesthetically acceptable. Other work that we are working is to have thermochromic materials that I'm not going to show you a lot about that, just ideas, and selectively emissivity with selectively emissivity properties, and also to combine cool materials with storage, PCM phase change materials, and also we are looking for combination of cool materials with photovoltaics, and this is an application we're going to do in this pro bono project, and I hope in 2 years from now I'll have more results to show you. So for that, I would like to thank you for your attention.
Department of Civil and Environmental Engineering, also Desert Architecture and Urban Planning. I work on energy, buildings, and people. And I hope I can get my own presentation up here. It's not a touch screen. איך אתם עובדים עם מסכים כאלה? האחרון. So I'll be talking about something in the same lines, more or less, of the previous presentations, but I'll be focusing on tall buildings. We call them skyscrapers, tall buildings, towers, whatever you wanted to call them, but we are talking about the same thing, and those buildings, energy, climate, safety, and survivability. The first tall building in history, the Tower of Babel, even before it was built, people started realizing that there was trouble with the tall buildings. This is from a synagogue in near the Sea of Galilee, a beautiful mosaic showing how people do not get along with tall buildings even during the construction phase. And I'm going to present a longitudinal study that we are working on for a number of years, a large group of people, research students, postdocs, and colleagues. Tall buildings have become the predominant building type around the world. What you see here is a graph of buildings above 200 meters tall. And as we move into an urbanization process that's becoming more and more accelerated, and as the population of the Earth grows, and as we consider quality of life things that are very extravagant, such as tall buildings, we get more and more all over the world. However, we keep forgetting that the higher up above ground we go, we encounter a completely different climate. And what you see here is on the left-hand side, the temperature difference at different altitudes during the year. The year is on the x-axis, and the temperature, the air temperature, is on the y-axis. And you can see that from the ground level, as we keep going higher and higher, the temperature drops by a significant segment of what we experience in the city. On the right-hand side, you can see that we also have a difference in wind velocity. The higher above ground we go, the higher the wind speed. And we took two building types, which are quite common in the center of Tel Aviv, but not only. You can find them in most of the Israeli cities, and therefore in most of the big cities of the world. On the right-hand side, you can see here an office building, and on the left-hand side, a residential tower. And we simulated their energy performance, understanding that what separates the outside with the inside, the outdoors with the indoors, is the envelope of the building and its thermal properties, its physical properties, and that makes a huge difference. So what we found for the towers that are very common around Tel Aviv, Ramat Gan, Givatayim, and all sorts of other cities, is that if we look at the upper graph, we see a huge difference between the heating and cooling energy demands as they differentiate from the ground level, which is, I'll be using this word device. Is that right? So what we have here is the heating needs of an office tower vis-a-vis the cooling needs of an office tower. And you can see that the higher up we go, we have less cooling needs than we have close to the ground. The same thing goes for the residential tower, yet the differences are huge between those two building types, building uses, because of internal loads, and not least because of the envelope of the building, most of the office buildings being hothouses, greenhouses, fully glazed from the ground all the way to the roof. So what did we find in this part of the study? Well, high-rise buildings, there are microclimate changes with altitude above ground, the building height, wind speed increases, dry bulb temperature decreases. This is the theory, but we measured that. We considered a climatically responsive design in skyscraper construction that takes into consideration four main variables: the design strategy according to the building's immediate environment, the orientation, the prevailing winds, the thermal properties of the building envelope, the effect of height on the energy performance, and the internal heat gains of the building, residential vis-a-vis the office building. The effect of the changing microclimate with height may become a positive asset in the building's energy efficiency all year round if the specific climatic conditions of the building's location are taken into consideration in relation to the design of the building's envelope, which we see that they are not. I will just be showing what we published as we go along because some of the work is still ongoing. This has already been published and is available. Our next step was to start talking about the energy efficiency of the building's envelope and how we can affect that. That's a tall building. This is a typical tall building envelope. Likewise here, the Technical University of Eindhoven, but we see something interesting here, as opposed to the previous two slides. We see an intermediate space between indoors and outdoors. And this has become quite common in many of the tall buildings, which have what we call a double skin facade that has an indoor facade that may or may not include openable windows, shading devices or not, and then an external, fully glazed skin that provides some kind of access just to clean the windows, more or less, but also maybe to mix return air with fresh air, etc., etc. We simulated 4 different double skin facades with different materials, and we reached this diagram over here that shows the extent to which we can influence the energy needs ranging by the height of the building above ground. And the idea is that the more dynamic the envelope of the building using a double skin facade, the more we can affect energy use, and that goes back to what Susan Roaf was saying earlier about natural ventilation, shading, etc. And to what extent can we really document that? Well, here you see the different heating and cooling needs by altitude with a double skin facade that can be manipulated and operated. And you see that the higher up we go, we get a very low cooling energy need, but huge heating energy load. And that means that maybe even double skin facades cannot be uniform, and they have to be redesigned and detailed by altitude above ground if we are to use them and make sure that we actually can have this kind of drop with the width of the double skin facade cavity. 20 centimeters here, 50 centimeters, 1 meter, and 2 meters, and you can see that there is a continuous drop, and of course that has projections on the financial issues of the construction of the building as well as municipal taxes, etc. So what we got was a preference for double skin facades in order to lower the energy demand, and we can say that if we use a low emissivity coating on the external surface, which is a practice that is not common in such glazing systems, we can drop the energy needs maybe by 15%. The wider this cavity that we have, the more energy efficiency or energy savings we can have. And we published all of those results, the research and the methodology in 3 papers, not least the Council of Tall Buildings and Urban Habitat Journal, which is not exactly a journal that is interested in energy conservation, but rather one that is interested in tall buildings. Our next step was to try and understand how the climate with altitude affects residential towers, and the office towers that we simulated earlier were these ones, the Alon towers in the central area of Tel Aviv and Ramat Gan, and now we are moving on to the residential towers that are just behind them. knowing that the higher up you go and the higher the velocity of the wind, the more problematic it becomes to use open spaces such as balconies. And what we see here is an accidental collapse of a glazing system in a residential building's balcony where a baby might have been playing there. But this is work in progress. We haven't published it yet. We are working on the last corrections of the paper. I will say that on-site monitoring at different height balconies, and I want just to point them out for you. These are the balconies that we monitored. Very low, middle of the building, windward, and in between two towers, and that makes a huge difference, and way high up. So what we have monitored shows that the environmental conditions vary extensively, and that when we juxtapose the measurements with the perception of the building occupants, we end up by understanding that these are very expensive but useless spaces, that people pay a lot of money for them but will never have any access to them because of the microclimatic conditions. While there are different parameters governing tall buildings relative to their height above ground, such as environmental, social, economic, etc., current design practices do not reflect upon such, with the use of typical floor plan design all along the structure's height being one of the examples. So we talked previously about maybe specifying different detailing for the envelope as we go up, and now we talk also about the design of the floor plan itself. The introduction of exposed balconies along the high-rise building envelope, a design, when we introduce exposed balconies, which seems to be something very common, it means that we are doing something that has not been previously taken into account, not least the fact that way high up, the wind velocity makes use of balconies dangerous, especially for small children, not safe also for elderly people. Tall buildings and their relationship to the urban environment should be studied from a holistic perspective. And this is the paper that we are working on, hopefully will be published soon. How am I doing with time? Okay, thank you. I'm just trying to quote from a book that was published a few years ago by Edward Glaser, Triumph of the City. And Glaser claims in this book that the taller and denser and deeper a city, the more people it can accommodate per area unit, the greener it is, as it counters suburbanization and urban sprawl and helps conserve more open areas for agriculture, leisure, nature reserves, etc. Thus, tall buildings are the typology of the future, says Glaser, and this is the translation into Hebrew of his book. This is not a lousy collage. This is an actual swimming pool on top of tower buildings in Singapore. Now, I don't have fear of heights, and I swim quite well. You could never get me in there. Going on with additional research on our tall buildings, we started investigating the microclimate, the urban climate under the buildings, around the buildings, where the pedestrians are. And we try to understand if these are spaces that are useful or useless, because most of those places have restaurants and cafes and boutiques, and the question is, will people use those spaces? So this is our case study, and this is our little monitoring station. We are measuring with two wind velocity and wind direction meters to make sure we get the right readings. We tried to understand if there will be any direct sunlight reaching that area full of cafes, etc., etc. These are office buildings, and office workers will go down there to have lunch. As you can see from the shading simulations, it's practically totally shaded throughout the whole year, which may be good for the summer, but we'll see what it does for the winter. Measurements of the wind velocity and the gust measurements, which is the very short period, significant wind-blown effects that we get. And of course, on top of that, we also have the air temperature. And we have on the left-hand side December for winter and July on the right-hand side for summer. And you can see that velocities in the wintertime, high wind velocities correlate with low temperatures, which makes thermal comfort much less acceptable or achievable. In the summertime, it's a little bit different, and what you see at the bottom is a series of pictures of people trying to walk around tall buildings, which would be cases similar to such gusts. Bottom left-hand side, Sultana Saroglu, a PhD student of mine, and then postdoc for a number of years, currently at the Technion, and Chofit Yitzhak Ben Shalom, ex-geography, BGU, and later on Porter School of Environmental Studies in Tel Aviv. These are the two Alonim towers, and we followed a certain trajectory, taking spot measurements of air temperature, wind velocity, and relative humidity, and the blue circles show the positions where we measured time after time. The bigger the radius, the stronger the wind effect. This is more or less what we concluded from our measurements that were followed with a survey with questionnaires that we administered to passers-by. We filled in during each one of the seasons nearly 300 questionnaires, randomly distributed. We wanted to know if people work and live there, or just work there, or just live there, or passing by, whatever. And we noted also clothing, and we noted also their responses to whether they came into that urban space from a previously air-conditioned space. We found some very interesting things. For example, that thing over here, I hope it can work. But we have no sound, unfortunately. And this is summertime. You can see, oh, there it goes. This is what happens down on the pedestrian level. Summertime, high temperature, high wind velocity may be positive, but the question is, how comfortable does it feel? And on the right-hand side, you can see, of course, why we get such wind velocities. Because when the wind hits the windward facade of the tower, you get a downdraft, which sometimes is much faster, much stronger than the original wind itself. And in between the towers, of course, you get a Venturi effect by trying to push a liquid into a very small section, so you get a very high velocity. This is what happens around tall buildings. So just to conclude this part of the research, tall buildings block wind that passes over the rooftops of the average height of building fabric and deflect it at a higher speed down to the street level, affecting pedestrian comfort. Predicting urban wind climate is not an easy task. No universal wind comfort criteria exist for pedestrians. To describe the complexity of outdoor thermal comfort conditions and create an understanding of the wind climate parameters, the subjective human perception, was included throughout the questionnaires that we administered. Where urban wind speeds are unpleasant, appropriate mitigation measures need to be implemented, which may include architectural features such as different walls and maybe canopies, etc., windbreakers, and built-up features that will enhance airflow where ventilation is considered appropriate or even necessary. there is need to better understand the relationship between urban design, outdoor thermal comfort, and specific climatic conditions, and I think all of the previous speakers focused exactly on these issues. Published in Building Research and Information quite recently. What we are doing now is trying to understand the air quality in between and under those buildings. This is where our case study is located, about 3 kilometers from the seashore of Tel Aviv. And we have a series of measurements of microclimatic and air quality data from 3 locations which are very close to each other, in between the 2 towers, in a residential area, low-rise construction just at the leeward side, and a bridge that is going over the main artery of the center of the country, that is Ayalon Highways and the railroad, and work in progress. But what we can say so far is that intense urbanization of modern cities creates thermal discomfort and deteriorates air quality. This is measured, affects the health and well-being of the city's inhabitants. We found high concentrations of particulate matter, 2.5, but also 10, which is hazardous. We verified the existence of urban heat island as well as high concentrations of air pollution due to intensive transportation and energy consumption, sometimes that happening in positions that were quite surprising, in between the buildings, sometimes way up. Pedestrian design practices need to be incorporated into building design strategies in order to mitigate potentially uncomfortable and unhealthy outdoors. A sustainable urban future needs to consider outdoor thermal comfort and air quality as vital parameters other than just real estate values. Coming back to Susan Roaf. Just to conclude, tall buildings have a whole array of other issues. They are tall, so they need deeper foundations. These are the foundations of the Burj Khalifa, 835 meters tall, and the Saudis are going for something even taller, 1 kilometer tall. Just try to picture it, a building that is 1 kilometer above ground. The piles that start underneath this layer that you see here go about, there are 194 of them, and they go about 47, 48 meters deep, right? But this platform is more than 3.5 meters of solid concrete. That's what you need in order to keep this beautiful tower standing up there. Now, buildings use about 50% of the overall energy we use in industrialized countries, 10% that go into the production of the building materials and the construction itself, and the rest goes into cooling and heating and lighting and ventilating those buildings. So buildings are a huge problem, but maybe they are also the solution. Tall buildings need more embodied energy, more energy into their production than lower buildings. And they need more operational energy, operative energy, for heating, cooling, ventilation, etc., than the tall buildings. And of course, when we build them like that, like aquaria, like terraria, we keep forgetting that the moment the user will go in, they will start shading the place because what we have created for them is an exceptionally uncomfortable environment, visually, thermally, even psychologically. Some of the better examples, thank you, I'm just completing, some of the better examples of tall buildings include the walkie-talkie building in London, which was designed so greatly by its architects that it has a parabolic facade that burns whatever is parked on the other side of the road. They create urban ventilation issues, they have stability issues that have to be very well thought, especially in countries such as this one that has a catastrophic earthquake every 80 years. Their facades tend to sometimes rain on the pedestrians broken glass, and this is the John Hancock Tower in Boston. And of course, we cannot forget other hazards, such as how do you evacuate people during a fire, during an earthquake, during a war. And I'm showing the Grenfell Tower, which was on fire in 2017 in Kensington. This is what was left of the building, and everything burned because the contractor saved money on the material for the cladding. Instead of using a material that will not burn, he used a cheap material that emitted hazardous vapors. So he saved about 300,000 pounds. But 72 people choked to death in this burning building. And we can calculate very easily the value of a human life, which is about 4,000 pounds, which is pretty cheap. Right. I want to thank all of those who have participated in this weird research and say that for the tall buildings we can have densification, profit, and ego. But against it, we have a huge array of other issues that we haven't really understood quite well yet. And there's Wolfgang and Denia and me up on about, I think, 250 meters above ground, trying to see if we can fly. Thank you very much for your patience. We have 8 minutes for questions for all the speakers. Do you want to come up on the podium, please? It will be easier. There are microphones there. Yes, any questions from the audience? Microclimate, vegetation, cool roofs. Yes, please. This is a very tricky answer. We can design appropriately with shorter buildings, still maintain open spaces that will be usable, not like the ones that we see now, which are unusable. And at the far end of the answer, the other edge of the spectrum, I say that if we keep on having a reproduction rate, which we have, in many countries, not even tall buildings will save us. So it's less people and a lower quality of life. What we consider a quality of life has to be something much more environmentally adapted, and then we can go down to normal height of buildings. Buildings of about 15 stories are still manageable. Buildings of about 50, 60, 80 stories, 100 stories, become a huge problem. And we don't know yet when they will start deteriorating because they will be unmaintainable. Yes, Alva.
You measure the amount of people walking in certain areas, but and you show different areas in Tel Aviv. But did you measure also, for example, if we have a street that we have in one side shadow and one side light or sun, what is the difference? Because sometimes, for example, in Kaplan Street in Tel Aviv, there is no shadow, there is nothing, and you have to go there, so you go, okay? So did you do something like this?
Yes, that was the, I would say the default option was comparing two sides of the same street. There are many problems. One is that the two sides of a street are, are not identical for many other aspects. There might be on one side a row of shops, of stores with inviting plate glass windows and many entrances, and the other might be a completely blank wall of an industrial building with no entrances. So we accounted for many differences like that. As far as Kaplan, that's sort of the poster child of what's missing in Tel Aviv, and one of the reasons that there are not more shade trees on Kaplan is that the underground infrastructure there next to the Kiria is so dense that it's actually quite difficult. So this is a problem that has been created, which is then difficult to solve.
Yes, please. Go there.
Denia, you mentioned combining cool materials with photovoltaic cells. I think this is impressive as it will improve the energy efficiency of this cool roof. But my question is, when you talk about standardizing the cool roof, is there a way you optimize the cool roof for maybe heating and cooling, or just the focus is to cool the building?
It works? Okay. The purpose should be to optimize for both heating and cooling, but needs a lot of research to overcome issues such as heating penalty. There is a lot of research efforts towards that, and we can find different types of buildings that cool roofs are applicable. I mentioned that also in the presentation. So yes, we should optimize, and I think there is something that, for example, is materials that might change properties between with different temperature, that is thermochromic or other type of materials, but they are not mature because the solar radiation has a significant effect of the properties characteristics so far, as far as I know. So there's nothing now that you can say that I can apply it for both winter and summer. I don't know if I answered your question.
Yes, please. Questions? Yes.
A question for Susan Roaf. You mentioned that the regulations and recommendations that are really product motivated. Have you seen examples of countries of specific regulations that successfully managed to not be?
Yes, I tell you where's absolutely brilliant. Anyone from Brazil? Yeah, Brazil is really good. And what you've got there is leadership. You've got Roberto Lam. Oh, okay. But in Brazil, you've got one or two individuals who create a research group, Roberto Lambert's, and they've done some fantastic work on the use of natural ventilation in Brazil, because you've got a fairly high proportion of very poor people there. So you don't want regulations like we have in Britain that lock you into having a product as a solution. So pushing you into having heat recirculation or you know, mechanical ventilation systems. So it takes a lot of leadership. But I would say, I would cite Brazil, and they've got some of the best research on it. But what we need is, I think we have a lot of people from Kenya and Africa. So really, it's something I said to the Minister of the Environment in India many years ago. I said, look, everybody in India seems to be wanting the American dream in terms of material things. What is the Indian dream? So what is the Kenyan dream? What is, you know, to sit on a lovely terrace outside the house with a nice shade over it, with a cool drink, and, you know, you have to, every country has to create its own reality of quality of life and comfort. And the last thing you want to do is accept Western European or American standards and end up in air-conditioned buildings you can't afford to cool or heat. It's controversial.
Any more questions from the floor, comments? Yes, please. Over there.
One quick question regarding these enormous buildings that we already have all over our cities. We can't tear them down. Well, we could, but it would be very controversial indeed. So, what kind of measures can we take now to the existing buildings? Is there something that we can do to improve the quality of the life of the people underneath and the people that are inside them?
Who, me? Okay. Well, we try to retrofit existing buildings, older ones, and I see no reason why not to retrofit newer buildings that are lousy in terms of their thermal behavior, energy consumption, microclimatic impacts, etc., etc. It will cost money because those buildings have very expensive envelopes. But on the other hand, if we run a cost-benefit analysis of how much energy we have to invest for their next 30, 40, 50 years of lifetime, vis-a-vis how much energy is needed in order to retrofit them, we may end up by deciding to retrofit them for the benefit of their users, the tenants, the benefit of the city, the benefit of the balance of the energy, the benefit of climate change, the benefit of all sorts of things that private developers do not really take into account.
Could I add on that? I started noticing in cities around the world in about 2000 what I call dead building syndrome. And it's usually, you can tell, usually it's 15 to, or maybe 10 to 20 story buildings built in the 1960s. And you see it in cities around the world, you know, from Istanbul to everywhere. And they're usually by the railway station. And people don't want to live in them anymore. They're concrete, they're single glazed, and they just sort of die. I mean, in some wealthier countries, like I noticed in Eindhoven, they do afford to refurbish them, but in a lot of cities, they just sort of leave that building and it sort of deteriorates and they move on to the fancy new shiny building business district. So I do think that just note in your own cities, if you ever see any of this sort of, it's a sort of cancer that spreads. So what will happen with the super talls? I've got no idea. Yeah.
In Hong Kong, which is full of skyscrapers, I saw a presentation once in which there was a proposal to remove a whole series of high-rise buildings in order to create a wind corridor to get better ventilation from the sea into the city. And I asked a local architect, an expert, if that's actually realistic to tear down buildings, high-rise buildings. And he said, of course, they're torn down all the time. Thing is that they're usually replaced with even taller buildings. And not only that, what happens to the materials from the demolished buildings? Basically nothing other than landfilling. If I could also add a point to Delia's questions about population density and high-rise buildings. There have been calculations done that show that if you compare the way these high-rise buildings are built in Israel, for instance in Tel Aviv, with very large spaces in between them, we call this the tower in the park syndrome, and that if you just compare the number of inhabitants per square kilometer, you can reach the same number with essentially medium height, medium density construction like in European cities. It doesn't seem to be happening in Israel. It's going the opposite direction for some of the reasons Sakis mentioned, because profit motives often outweigh other considerations, but we can see all over the world that cities that have high-rise buildings, it's not because they have the highest population density. There's a high density of capital. And final word about products and everything focusing on marketable product. Somewhere around 1990, there was this sort of marriage of convenience between environmentalists and business people. The magic solution was sustainability. That everything, all the solutions will be both profitable in the short term, it'll make you rich, and will be environmentally positive in their impact in the future. So this is a very nice idea, and in theory, it's really ideal. But oftentimes what we come out with is some of the things that Sue showed, that we're just perpetuating products, systems, solutions, which can be marketed, and believe me, it's very easy to market something as green. There are very talented people doing that.
Right. If we don't have anything urgent and pressing, I would like to thank my co-panelists, Professor Denia Kolokotsa, Professor Ursula Eicker, Professor Susan Roaf, and my colleague, Professor David Pearlmutter. And thank you all very much.